Thank you all for coming. So first, if you have any questions, just ask them in the chat, and I will then try to answer them right away, or I will do this at the end if you have enough time. So yeah, as already mentioned, I will show you something about Java 21 and how its virtual threads really change the way we will develop our further applications. So the first thing, a small introduction about me. My name is Christian. I've been working as a full stack engineer for the last 12 years, started with Java 6. And since around 7 years, I'm also doing quite some full stack work with Angular, TypeScript, and JavaScript. So the topics I will show you today are like four little building blocks. We will start with an empty Spring Boot application. We will then create a blocking application. We'll then change it to reactive, and we'll then change it again to work with Project Loom. And at the end, we will see a small conclusion. So first, about the blocking API. Well, basically, many of us, I think, are still using the blocking API. So are still using like the REST template in Spring Boot, or like the blocking APIs all over Java. Why is this? Because we are still like in this time of the blocking early days. For us, it's nice, it's working. Why? Because basically we are not like the Netflix or the Amazons, and we don't really need this high throughput. We basically have like small applications which have like 30 users or 40 users, which are running concurrently. So you don't need this huge throughput. So now let me show you how we can create such an application really easy. So I'm here in IntelliJ. So the first thing we do here is I will create a new controller. So let's call this JCON controller. And we will say we have, of course, our REST controller here, and we have our request mapping, and let's call this /API. And what we now do here instead is we have our get mapping, and we will fake like an API where we want to return the current speakers of the JCON. So what we can do here is first we have our record here, and we say we have a speaker, and the speaker has a name. Now this get mapping here says /speakers, and we say we want to return the speaker here, and let's call this get speakers. Now, of course, we have to create like a small service to call our HTTP endpoint. So here I will say private fake HTTP service, because I will not do a real HTTP call, but I will fake one with a service we create. So let's go in and say we want to create this fake HTTP service like this. And we say add service. And now we can go back into our application, and we just say return fake HTTP service, retrieve speakers blocking, like this. And we have, of course, to create this method. So we return our speaker. Now, important here is we want to have like this delay. How do we do this how do we fake this? We say thread.sleep. And basically, this is the same thing that would happen if you do a REST template call. It will then block the thread. And as soon as it's at the input-output response is given, then we can go further with our request. So we have our final list here of speakers. Let's call this speakers. And let's say we have 10 speakers. And we say map to object. And for each of the indexes, we create a speaker, and we have our index there. And now we have the list. So what we say here is we just return the speakers, and now our code compiles. So I will go in there and restart and start our virtual threads application like this. So what we now can see is our application started. Now let's go in there and let's go into something called JMeter. JMeter is a tool to check how many requests we can send in a certain amount of time, and if there are like delays in there, and how much the response time is. So I'm here at the HTTP loads, and I say I want to call the /API/speakers endpoint. So let me now start this. And what this does here is it starts 1,000 threads. And as soon as they are started up, they call 1,000 requests simultaneously for 10 seconds. So these 1,000 users will now call our endpoint all the time. And we can then see what the response time of this result here is, of these calls. And we can see here, this response time graph starts at 1 second because there all the threads are still available, but it goes up to around 3.2 seconds. Well, why is this? Tomcat only has like a connection pool of 200 threads at max, if you do not change it otherwise. So this is why when all the threads are busy, we cannot process new requests, but we have to wait. So, but let's now see, why don't we just create as many threads as we want? Let's see if we do a test here. So we have our test, and what we say here is we want to create, let's say, 1,000 threads. We have our thread here, and we then say we have our threads, and we have our in stream again, and we say we want to create 1,000 threads. We have our map to object, and we have a new thread we create, and in there we have this lambda where we just want to do our thread sleep. So let's create a safe sleep so that we don't have to wrap it all the time and try catch. So we have our thread.sleep, and we pass in our milliseconds like this. And now we can just call it like this. Let's call this with 20 seconds and change it to list. Now we have, of course, to start all the threads. So we say for each, and we say thread start. And now for each of the threads, we have to wait until they are done. So if we do this, basically, we can start it. And we can, before I do this, I go into my terminal. I have a small watcher where I count the current threads which are running which were started from the JVM. How many operating system threads are running? We can see these are 116. I now start the test here. And what we now can see here is, if I change here, we can see now 1,000 threads got started. So, but why is this? The problem is, if we, until Java 21, started a normal platform thread, and these platform threads are basically the ones who are created from operating system, are basically a one-to-one mapping to operating system threads. So when the JVM starts a thread, it basically creates an operating system thread, and the platform thread is just like a small layer on top of it. So, but why is this really a problem? Let's see what happens if I change this here to 1 million instead. Now, let me change this to 1 million and start the test again. And what we will see is an out-of-memory exception really fast, because what we can see here is we get an out-of-memory error because the stack size here is 2 megabytes. And why is this a problem here? Let's do some basic math. Why can't we just use more threads? One thread basically needs around 1 to 2 megabytes of memory. It depends what the stack size is. But if you have like 1 million threads, it would take 1 terabyte of memory. And what this would mean that you would have for like 1 million threads, 1 terabyte of memory available all the time, only for like your one Spring Boot program. But you would have to have 1 million threads to have a CPU usage of 100%. So maybe you're thinking, well, what do you mean with the CPU usage? Well, let's think about how the thread we are currently using really uses the CPU. Let's say we have only one thread, and a request comes in, and the problem is the request comes in, we have to then send our HTTP request to another server, and the waiting time for the response of this HTTP server is in the hundreds of milliseconds. But the work the thread really has to do is in the matters of nanoseconds, because the deserialization and creation of the request is such a short time. So the thread is just idling all the time. And this is why many like high performance services were thinking, well, we really need more threads, but we can't create more threads. So instead of this, they would have to think about something different. And this is where they chose reactive. So what really is reactive? How does this work? Well, reactive is in Java for quite some time. And if you have worked with Spring Boot, for example, you also have seen reactivity, for example, with Spring Reactor. But let's see how we can create our endpoint in a reactive manner. So the first thing we do is we say we have a get mapping again, and let's call this speakers async. Now, instead of returning a list of speakers, what we do is we return a list of completable future. So we wrap our list in a completable future. This is something from the JDK itself. Of course, I could use Project Reactor, but I want to do this as framework agnostic as possible. So we have our speakers async here. And now what we say is return fake HTTP service, retrieve speakers async. And what we now can do is, of course, we implement the same function as before. Now, we can see here this returns a list of speakers. Now, because this is reactive and non-blocking, we can't use the thread sleep like we did in retrieve speakers blocking. But we can use completable future supply async. And you always have to think about this is just like a fake from my end. You, of course, otherwise would just call like with a web client to an HTTP, which then would return a completable future. But I will fake this. And so we say supply async, we return the speakers. And now what we do is we also want to have this delay of 1 second. So we say completable future, delayed executor of 1000 milliseconds. So this way we have like the same delay as with the thread sleep. Now, what we can do here is we just restart our virtual threads application like this. And what we now do is we can see it already restarted. We go back into our JMeter and we call speakers, but with async. And what now difference is we are now non-blocking. So the completable future API is now used to do the calls. And so we are not blocking these threads, but they can get reused. So we have like a thread pool, but the thread pool is not blocking as soon as we send this request. So what we can now see is, if we check for the response time, we can see this takes 1 second because we are not limited by the amount of threads, because as soon as this thread is sent over the wire and blocks basically, then the thread will no longer be in use and someone else can use this thread. So, well, this is really, really easy, looks really cool. But let's say we have some more complex approach. Let's say we have a talk and we have, this is the title here, and we want to have for each speaker his talk. So we can say get mapping and we say talks like this. So for the blocking approach, this is quite easy. We say talk here and we say get talks. We then say fake, we then of course have to take our speakers first. So we have our speakers. We call fake HTTP service, retrieve speakers blocking. And then we can just say speakers.map. And for each speaker, we call fake HTTP service, retrieve talk, where we send in our speaker. And we then pack it into a list. So, of course, we have to create this retrieve talk, but this is also quite easy because we just have to return a talk. This way, we just say thread.sleep of, let's say, 500 milliseconds. And now we return a new talk like this. And we say talk for speaker. And we have speaker.name like this. So, and this would work. But the problem is this here, even if you would have no delay, this takes 1 second. And this here would take 10 times 500 milliseconds, which is 5 seconds. So even if we would have an endless amount of threads, this would take 6 seconds all the time. So, but how can you do the same thing with reactive? So let me show you. The first thing we do is we create a get mapping. And then we say we have our /talks. Let's call this async. And now we have a completable future, which wraps our talk, our list of talks. We have get talks async. And now we have to do basically the same thing like in get talks. We have speakers async, fake HTTP service, retrieve speakers async, because we can never break this reactive chain. And what we now have to do is we have to have like a nested so-called like a callback, because we say return speakers async, and now we have to choose which function we need. And we can see here we have then apply, handle async, then combine, and so much more stuff, which we always have to keep in mind what these functions really mean. But in our case, we use then apply. We have our speakers here, which we as soon as we get them, we use them. And what we now say is we have a list of completable future of talk, because for each of the speakers, we say stream here, talk futures here, we have our speakers, and we have stream.map. And now for each of our speaker, we have to call fake HTTP service, retrieve talk async, because this has to be async as well. And then we collect this. So we say our retrieve talk async. And now what we return is a completable future of talk. Now we can use this completable future supply async up here. Just copy this. And we can use basically the same approach as with the retrieve speakers async. But instead of returning speakers, we return a new talk where we say async talk from speaker.name, like this. Now we can see this works, but the problem is we don't want to have a list of completable futures, but a completable futures which has a list. So what we have to do is we have to say return talk futures stream.map, and now we have our completable future join, and we have to have a list from it, and then we can return it. And we can see here this is working, this is okay, but the problem is, even if I say this is here basically a var, this is still nested, and this is still a simple example how you can work with this. But you can see the difference between the get talks, which is synchronous, and this talks async is quite huge. So now let's talk what really are the problems now with reactive. Don't get me wrong, I really like reactive because I'm also like working heavily in the front end, and we all only program there reactively. But even there we have seen that like this callbacks and this nesting isn't really what we like. So we even switched there to like this async await style. And here with this, the problem with reactive basically are like four things or three things which are combined into one. First, it's hard to write because you write a lot of unnecessary code, which you basically should not have to care about. It's also not easy to read because the learning curve is quite steep. And because of that, it's also hard to test because your business code basically gets almost secondary because you wrap this in all this asynchronous framework code. And last but not least, the compatibility. You have to be compatible with reactive until the database, because you need R2DBC drivers to also have reactive database support. And what I dislike the most is you have many different implementations, many different frameworks, all have different namings, all work differently. And in this case, you have to relearn so much stuff because things work differently in different frameworks. So many of us are now like in their reactive later days and say, this is nice, this is fast, but it is also way too complex. And also the people from the JDK were thinking, yeah, this can't be like the end of our, how we will program for the next 100 years, basically. And they were thinking, well, we have to think about something else. And this is where Project Loom came into play. So Project Loom was developed for the last 4 to 5 years. Sometimes it was called Project Fiber. And the basic thing they were thinking of, well, what was the problem back in the beginning with this blocking stuff? The problem was that they needed more threads. They needed possibility to create more threads, but this is what was not possible. So they were like, checking, well, how many threads do we want? And they were seeing, okay, we need at least 1 million threads. Why? Because if you have less than 1 million threads, the reactive approach is always faster. Because if you have like 500,000 threads, then reactivity can still have one 500,000 more threads in the meaning of that it's much faster. So you really have need to have the possibility to have these 1 million threads. And the solution to this problem were virtual threads. On a basic level, what are basically virtual threads? Virtual threads are like an own construct which is handled in the JVM and is also like much lighter than a platform thread. One virtual thread is in the sizes of kilobytes, where a platform thread needs like megabytes. This is also why you can create almost 1,000 times more virtual threads than platform threads. But how does this work? Let me show you. So let's say we are now in our request with the speakers. So somebody calls our endpoint /speakers. What we then do is we like create this request we want to send to this fake HTTP endpoint, which is normally, of course, a normal endpoint. And as soon as this blocks, so as soon as the request is sent and we are waiting for input-output, this virtual thread does something called a continuation yield. So there is an underlying object called a continuation, which basically says, okay, as soon as I block anywhere where the thread is basically idling, I send a so-called yield. And because of this, I can then unattach from my worker thread. And it will then go and will be moved onto the heap. And so at this time, this worker thread is free to do other stuff. And because these worker threads are like a small number of platform threads, basically in a fork join pool. But as soon as the response comes back and the operating system signals that the output is available or the input is available, we need to work further and send the response to the caller of our speakers endpoint. The virtual thread will then use this continuation and will be attached to another worker thread. So we can maybe see, you maybe have already seen it, this is not the same worker thread than before, because the virtual thread is not fixed to one worker thread, but it can choose which one is currently available. So let me show you how this works in code. So we are back in IntelliJ, and let me show you how these virtual threads work. We can see here I have this 1 million threads, which caused an out-of-memory exception. Now, instead of saying we want to have a new thread here, what we say is we can use the new factory methods on the thread. So we can say thread dot, and we can say off platform, which creates a normal thread as we know it, or off virtual. So we say off virtual like this, and we then say unstarted, because we want to create an unstarted thread. And this is basically it. And as we can see, this is still a normal thread, because beneath it, the virtual threads are extending the normal threads. So for everywhere you use normal threads, you can also use virtual threads. So let me now show you what happens. I now start with 1 million threads here. I will start this test. But before, I will just start my count threads here. But let me just show you count threads from Java. We can see these are 117 threads which are running. Now I start these 1 million virtual threads. The first thing we see is that we don't have an out-of-memory exception. The second one is, if I count threads from Java, we can see this only created 45 threads. Because, as already mentioned, they work on some work, the virtual threads are on top of worker threads, which are not needed to be like in the hundreds. They are just needed to be like in the amount of 50 or 60 threads at most, and because they are not always busy. And we can see here, now it's done, the test is done. And if I check now, we are back at 118 threads. So, but let me show you that this really works like a normal thread. So instead of this sleep here, I say if the index is 0, because we want to access one explicit thread. So we want to have like the thread 0, we say thread.current thread, and we output the value of our current thread. And what we then say is thread, we have a safe sleep here of 20 milliseconds, and I just copy this 2 more times. And now let me rerun this. And now something interesting happens. We can see we have here the virtual thread with the number 22 all the time. So this is the same thread, but it's running the first time on worker 4, then on worker 5, and then on worker 7 of this fork join pool. So the cool stuff about this is we can see that it changed between the worker threads because of this thread sleep, which is called. It then unattached, it's packed, is copied on, is moved onto the heap, and then it gets back and searches for another available worker. So, but how does this work? Well, let me show you the sleep function here. This is the normal thread sleep we all know, but this here is special. See this try final here. We see if the current thread is a virtual thread, then use this sleep nanos. Otherwise, use the normal sleep 0 function. And the cool part about this is everywhere you were currently using threads, the people from the JDK had to put in compatibility with the virtual threads as well. So if you check the pull request for the change to the JDK to enable virtual threads, there were over 100,000 changes in the code because you had to change this everywhere to make it compatible. So they also changed it for example, NIO for the files API. They changed it everywhere. They were using threads before. They are now also using virtual threads. So let me show you how you can easily use this in your existing application. So the first thing you do is we are here in Spring Boot. Now, I'm on a special version of Spring Boot, namely on the release candidate for 3.2.0. And the cool thing about this is it makes it really easy to enable these virtual threads. So I can just go in the application properties and say spring.threads.virtual.enabled and say true. Now, if you are still on, of course, not on release candidates, then you would have to override the Tomcat executor service. And basically, you can do this everywhere you are using normal threads. You could then say, we have here the executors dot, and now you could, the normal Tomcat used a connection pool, like a fork join pool. But for the virtual threads should never be pooled. So they should always be used once and then thrown away. So of course, because of this, we can use the so-called new virtual thread per task executor. And this is an executor service which can be used everywhere where you used an executor service with a thread pool prior to this. So you would have to use this in Spring Boot version 3.1.5 or earlier. But of course, because we are here in the release candidate, I can just say virtual enabled true. So I now restart this application. Now we see it already restarted. Now let me show you JMeter again. Now I have not changed anything in my code. But what I do now is I change this back from speakers async to speakers like this. And I just rerun the code. And this is basically exactly the same thing as before. We start up 1,000 threads, 1,000 users, and just send the requests against our endpoint. But now we will see quite a difference in speed and in response time. So let me show you how this response is now done. And we see here we have a graph of 1 second throughput all the time. And why does this happen? It's really easy. So let me just go back into the code and let's go through this. So our endpoint gets called with get speakers. This now calls like our fake HTTP service, which would basically call with the REST template and do a blocking call. As soon as this thread sleep, and basically this is the same, as soon as the thread blocks, as soon as the virtual thread blocks, it will unattach from the worker thread and will now give this worker thread available for another virtual thread. So because of this, we are never blocking like this fork join pool of workers. And this is why we can have so many concurrent requests. So this is really easy done with the simple approach here. But what would be the change here we would have to do to also make this get talks faster? Because always think about this. This here always takes 1 second because we have this thread sleep of 1 second where we fake this delay we have from the response. And this here always takes 10 times 500 milliseconds, or x times, which x is the amount of speakers, because even if we have no delay because we have not enough threads, this always takes 6 seconds because we are not using parallel here. But the problem still remains, if you have a parallel stream, you can still block the parallel streams. So you should never use parallel streams with virtual threads. What you should use instead are so-called structured task scopes. Well, what are structured task scopes? Structured task scopes are a construct which is not available in Java 21, but it's enabled as a preview feature. And in Java 22, you will then be able to use it like in a normal application without enabling the preview. But let me show you how this works. So first thing we do here is we say we create a try block and we have a scope, and we say we have a new structured task scope. A structured task scope is something called like an executor service, quite similar to executor services. And what we then can say is we say this is a structured task scope which takes talk tasks. So what we now can do is we can basically take this speakers stream here we have and just copy it. And now we say we want to have a list of so-called subtasks. These subtasks are basically just for each subtask, there gets a virtual thread created. So we have a list of subtasks, which are talks, and these are our talk tasks. And now we can see here, of course, this does not work because we are returning a talk here in retrieve talk. Now, instead of this, what we have to do is we have to wrap our retrieve talk in our scope. So we say scope.fork, and by using scope.fork, we create a new task, and for each of these tasks, a virtual thread gets created. So we say, okay, for each of our forks, we want to have our retrieve talk function called. As you can see now, this compiles just fine. And now what we can do is we now have all the subtasks started. So they are started concurrently. So for each of this for this retrieve talk calls, a new virtual thread gets created. Now we can say scope.join because we want to wait until all the subtasks are done. And we can see here we have this join until. We could also say we want to have like a deadline until we wait, but let's use join because we know that we are done in quite fast. And after this, we can say, okay, and now we want to collect the result of these talks. We can say return talk tasks, and each subtask has a state. So we could also check here if the talks if the tasks were successful or failed or even unavailable. But in this case, we just say we map and we say subtask get because we want to get the result to list. And we can see here this now works. We remove this code here because we don't need it anymore. And now we can do is we just restart our application. So what we now hope for is that we take 1 second for the speakers here and half a second to run all these retrieve talk requests concurrently. So let me show you back in the JMeter here. We remove all that and we just call the /talks API. And let's just run it. Now, let's think about what happens is the scope here. For each of the speakers, we call this retrieve talk, but this is still blocking here. You can see we have not wrapped it. It's just wrapped by this scope fork to easily call it basically, it is blocking, but with the virtual threads. So we now can check back. We can see it's done. Let's see the response time, display graph, and we can say it took 1.5 seconds to run all the requests, because it's run concurrently on the virtual threads. So I really like this approach, but of course somebody now says, yeah, well, but this also has some boilerplate in there. It is not that nested like here in the completable future, but it has still some boilerplate. Yes, it has, and so we can make it even more concise. So what we can say is the structured task scope can be extended. So, and this can be done quite easily. Let's say we have our talk scope and we say extends structured task scope. And we say we want to pass in talks here. And now there is a function which we can override from the structured task scopes, the so-called handle complete. Handle complete will be called each time a subtask is done. And so we can see here, for each subtask, we can now collect the result. So we have to do this in a concurrent way. So let's say we have like here a collection, which is, let's call this a collection of talks, and we have our talks here, and we say new concurrent linked queue because we want to have a concurrent collection. And what we now can say is each time we call that this handle complete gets called, we say talks.add and we say subtask.get, because this way we get the value from the subtask. We could, of course, also check in here if it failed or if it was successful, and then create like two different queues or two different collections, one with the errors, one with the successful ones. But let's keep it simple this way. The next thing we do is, let's say, get talks. Let's call it like this, get talks. And now we return just the talks we collected. Of course, we have to make sure all the subtasks from this structured task scope are done. So we have to say super.join to join all, to wait for all the structured tasks to the subtasks to be done. And then let's do super.ensure owner and joined to make sure that we are the owner of this scope, and we are also have called joined. Now, this is already everything we need. So what we now can do is, let's go back into our code here, and we don't have to use the structured task scope anymore. We can use our new our talk task scope. But just a quick side note, you can also use some structured task scopes from the JDK, for example, shut down on failure or shut down on success, and they will shut down on the first failure or shut down on the first successful result. But in our case, of course, we use a so-called talk scope like this. So if we use this, what we can do here is we can say we don't need this assignment here anymore. We don't need the stream map anymore. We only need a for each, and we don't need this to list anymore. And we don't need to use scope join because we only have to use here scope.get talks. And now we can change this from a list to a collection, of course, and it still works as before. Let's restart the application. And we have one question from Danielle. Are structured tasks the way to go when it comes to start virtual thread? Virtual threads? Yeah, so you don't really have to basically, as for now, you don't really start threads yourself, right? You are basically, like as mentioned, you are using, for example, execute the service. So of course, as here, you can use and you should use as such structured task scopes to basically start your own virtual threads. Yeah, because currently you're using like an executor service because you should never be like having to handle these threads yourself. Well, so yeah, you're right. You can of course do it this way. You can also use like this executor service, but it is really the way to go because you're only running a virtual thread basically once and then throw it away. So yeah, it can be really used that way. So we have started the application again, and let me now show you just, if I rerun this application, what we can see here is, I have not changed anything, that we will see that it's exactly the same as before, and it will be done also in the same amount of time. So now we can see here, this is now much more concise. This is like 4 lines of code, and the coolest thing about what you should never but you always should think about is this retrieve talk here is still blocking. So the next question is, can you explain the pinning issue when you have, for example, a sleep call inside a synchronized block? I will, Pavel, I will show you this right. The next topic will be about this. So before we go back to the application, we can see here we have still 1.5 seconds. So the talk structured task scopes work exactly the same. So yeah, but now let's go, Pavel, to your question. So first thing is, if I wanted to say before this, what is with thread locals? Thread locals work exactly the same as before. You can use just thread locals because they are just normal threads. You should think about thread locals. How do you use it? If you were using it like Tomcat, where you create heavy objects in these thread locals, then it maybe is not the best way to use thread locals. You could then use so-called scoped values, but there is like, this would be a whole nother talk. But for things like passing around logging, you can easily use logging information. You can easily use thread locals. And of course, you could also use it to create these heavy objects. But because you do not pool virtual threads, you don't have to use these thread locals for this. But of course, you can always use thread locals. They work as before. Yeah, but now to the restrictions. And one question in the chat from Pavel was also one of the restrictions I wanted to show you, synchronized blocks. So Apache Tomcat had a main issue about synchronized blocks. The problem was that in a synchronized block, the virtual thread is pinned onto the worker thread. And so they cannot be unattached. So if you have such synchronized blocks, and this is important, and there is heavy IO tasks in there, if there is just like, if it goes through there really fast, you don't have to worry about this. But you can always replace your synchronized blocks, and this was done by Tomcat too, with so-called reentrant locks. Reentrant locks are a structure from Java, which basically does the same as the synchronized blocks, but they also are able to handle the virtual threads correctly. So like Pavel, hopefully this answers your question. So this is basically the problem and also the solution, how you can handle these reentrant locks. Second one is about native calls. Native calls have the problem that if you call into C or C++ code, you can this way access memory addresses. And because of this, the virtual thread is also pinned on the worker thread. So there is currently no way of doing this otherwise, because we cannot just move memory stuff around if we have to think that there maybe is an access to this memory. Third one is CPU heavy tasks. And maybe this is like a no-brainer, but we always have to think, why did we use virtual threads to start with? Because for IO tasks, we don't want to block the thread. But if you have a thread which does some CPU heavy task and does really heavy tasking in there, there is no speed improvement, because we really need, because the virtual thread will be as busy as another thread. So let's come to the conclusion. So basically, with Java 21, we really can make blocking great again. It's a real alternative to a reactive, because you can also do a really easy proof of concept. You don't have to rewrite your whole code base into reactive. You can just switch an execute service or switch it in Spring Boot and see if everything still works and if everything is faster. Third thing is it's done in the JDK, what for me means we don't have like this huge amount of different frameworks, and it's done nicely in the JDK, so we don't have to relearn everything. And the building blocks we have are also much less complex, in my opinion. And last one, we have less boilerplate. We can see we can wrap this structured task scope, extend it and reuse it, and make it really easy to use for us. So yeah, we are now on the timeline at Java 21. We made like a full circle from blocking back to blocking, but with much more power, with much more threads. So we have like this new kit on the block, and we don't know what the future will bring to us, but I think Java 21 didn't, and the people in the JDK did an awesome job providing this functionality without having us to rewrite our whole code. We can just switch to the virtual threads and everything should work as before. Yeah, so we would go now to the questions. If there are any more questions, I would be glad to answer them. Otherwise, if you have other questions, I will see at the end, you will see what how you can reach me. You can just find me on Twitter or on LinkedIn. If you want to just get in contact, send me a message there, or on my website, you can scan this QR code. And yeah, it was great giving the talk, and would be great hearing from you guys if any of you need some help or need some support. Andres, can you share the code? Yeah, of course. I will add this to my you can scan this QR code, and you can then come to my website, type.rocks. I will put it on my GitHub. It's not up there right now, but I will share it and put it on there. So yeah, it will be on there like in around 10 minutes or so. Cool. So I would thank you for all the for the questions. It was really nice. So yeah, I will now give back to the moderator. I have one more. Do you know if the pinning during a synchronized block will be changed in future versions? I don't really know. Maybe they will not, don't want to touch the synchronized stuff, because it's like, this is really old and it's like a construct from Java itself. I don't really know, but I think you can be just work great with the with the re-entrant lock instead. Yeah.